Welcome to the Space Telescope Public Lecture Series. Tonight's talk, Year 2 in Review, Groundbreaking Science Discoveries by JWST, presented by Macarena, Garcia, Marin of the Space Telescope Science Institute and the European Space Agency. I'm your host, Dr. Frank Summers of the Office of Public Outreach here at STScI. And as always, thanks to our wonderful tech team, tonight Gary Gilbert joins us, and Grant Justice, as usual, will be here handling the streaming to YouTube. Our upcoming talks. Next month, September 3rd, we will have a talk on the Roman Space Telescope by Ori Fox, also of STScI. In October, we have the feared TBD. I have not scheduled a speaker for October 1st, but don't worry, I always do. It's summertime. It's hard to get a speaker to commit in summer. So now that it's August, I'll be able to get somebody to commit for the fall. And on November 12th, note that that is the second Tuesday because we, of course, have Election Day on the first Tuesday in November here in the United States. There is Light in the Darkness. And this will be presented by Elena Vardulaki of the National Observatory of Athens. And when I do schedule that October 1st date, you will find out on our website, www.stsci.edu/public-lectures, where you can find in the lower left the links to all our webcasts, both on our STScI recordings as well as our YouTube playlist. And you can see in the lower right the box where you can enter your email address and subscribe to our twice a month emails about the lectures. Also on the website are the list of the upcoming lectures. And if you click on any one of those, that read more button, you will get the full information of the description about it, as well as links to the STScI webcast and the presentation on YouTube. As I said, for email, you can sign up at our website. That's the easiest way to sign up for our announcements. You can also subscribe to our YouTube channel, youtube.com/Hubble Space Telescope, all one word. And when you do that, you will get the new video notices as well as reminders of the live events. If you have comments or questions, you can send an email to publiclecture@stsci.edu. And finally, our social media. We do the social media accounts for the Hubble Space Telescope, for the Webb Space Telescope, and for the Space Telescope Science Institute. And we are on Facebook and X and YouTube and Instagram at the handles located there. Now, our news from the universe for August 2024. Our story for you tonight: an intermediate black hole in Omega Centauri. All right, so let's start talking about black holes, because black holes have sort of changed over my time presenting astronomy out to the public. And originally, we would present them like this, as these big funnel-shaped warping of space-time, sort of infinitely deep warp of space-time, okay? And this is meant to show the fourth dimensional distortion in a three-dimensional space-time. And that's how we always pictured it, because that was the vortex feeling of everything going down into a black hole. But then there was this movie called Interstellar. And since that time, we have now depicted them more astronomically correctly, using the general relativistic view of a black hole with all the material spinning around it, and the correct gravitational lensing so that you can see the far side and the underside and around it, and you get this wonderful presentation of it there. And so this is how people start to imagine black holes, now how they're depicted in our presentations. But we now have actual observations of a black hole. And what a black hole really looked like is an orange donut, right? This is from the radio astronomy observatories located across the globe that pulled together to be able to form what's called the Event Horizon Telescope, and that we can see the material around a black hole, that same sort of structure that is depicted in that interstellar type presentation, but seen in very, 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 very high resolution using radio telescopes. So we now know what a black hole see. But this is only possible with sort of a planet-wide radio astronomy array. What can a simple space telescope or other ground-based telescopes do in terms of observing black holes? Well, the black holes that we can see come in two basic varieties. One is a stellar mass black hole. So that is a star that has imploded and become a black hole. But we can't see the black hole itself unless it is in a binary star system and there's material that streams off around that star, circles around that star, and funnels into the black hole. We call this a cataclysmic binary star system, okay? Or X-ray binaries, because they often emit in X-rays, okay? So you got a star system where you got a black hole and another star around it, then there's enough emission from around the black hole. Again, nothing comes out of the black hole itself, but there's enough emission from around the black hole that we can see these stellar mass black holes. The other case where we commonly see black holes is in galaxies, very large galaxies. This one here is Messier 87. It's a giant elliptical galaxy. Get the word giant, really big elliptical galaxy. And in the center, you can see there is a jet coming from it, okay? There's a supermassive black hole in here that's more than 1 billion times the mass of our sun. This is a billion solar mass black hole, and materials funneling into shooting out in this jet that stretches across on galactic scales, right? So these jets indicate where there are supermassive black holes in these giant galaxies. All right. So you got stellar mass black holes and supermassive black holes. Well, actually, there is a third type that we have seen very few of them in other places. And one of the places we've seen them is a globular star cluster, Omega Centauri. This is one of the largest star clusters in the Milky Way. It's about 10 million solar masses. Actually, it kind of resembles a very small galaxy, 10 million solar masses, stars orbiting around one another, okay? This is a beautiful ground-based image, but Hubble actually can view this as well, and Hubble has much finer detail. Uh, this image I'm showing to you right here is almost 14,000 by 14,000 pixels square. Yeah, that's a huge number of pixels up there. And actually, we can get in a lot of detail. Here is a pullout of it where you can see that we can see the individual stars in this star cluster that's 17,500 light years away, okay? We can look at those stars in immense detail to look at those stars. Now, this isn't the first time that Hubble has looked at Omega Cen. In my time here, I remember a result that we produced in 2001, and then we had another one that we came out in 2010, and then we had this one that just came out recently here in 2024. That's several decades of time looking at the stars in Omega Cen. And what we've done here actually is we've assembled a database of more than 1 million stars and their positions at these different times across decades, right? So there's over 1 million stars in a database of where they're located at different times in from Hubble observations. So this is a rife database for looking at the motions of stars within Omega Centauri. And researchers went through it looking for the needles in the haystack, the crazy things that might indicate something unusual. Well, they found seven, seven stars in there that are moving so fast that they should not be there because there's a certain mass to Omega Centauri, and if you're moving so fast, you're actually just going to spew straight out of it. You're no longer bound to that system. But they found seven stars that are in the core of the galaxy and are bound to the system. Right? Well, what does that mean? That means that there must be something holding them in there. And the best explanation for those seven stars is a very massive object keeping them bound in the core of the cluster. And that would be a black hole of about 8,000 solar masses. All right, so here's what we did. All right, this is our new result that in the globular cluster of Omega Centauri, we've been following it for decades, and in it we find stars that are moving so fast that they indicate that there is an intermediate mass black hole in the core of Omega Cen, right? Because we had the stellar mass of up to like 100 solar masses, and they had the supermassive, which are millions and billions. But here we have thousands of solar mass black holes. And this is really special because we have only found three, four, five, as far as I know, indications of intermediate mass black holes. And the question that astronomers naturally want to ask is, how are these three different levels of black holes related? I mean, do you start out as stellar mass black holes and then grow into intermediate mass black holes and then grow further into supermassive black holes? Or do the three things all have separate formation processes and they're not quite, evolutionary related in some way? There are a lot of questions about these intermediate mass black holes because we've only discovered a few of them. But new evidence from Hubble indicates that there really is, almost assuredly is, an intermediate black hole in Omega Centauri, and it will continue to be studied for quite some time. All right. Now, our speaker tonight is Macarena Garcia Marin. She is the project scientist for the Webb Space Telescope mission here at the Space Telescope Science Institute. She got her undergraduate degree in the Canary Islands, and then did her PhD at the University of Madrid in Spain. She did postdocs in Germany with a bunch of traveling around the continent. She came over to the U.S. One time during that period of her life, where she also worked very hard on the mid-infrared instrument that is on the Webb Space Telescope. When she came here almost a decade ago, she was the head of the mid-infrared instrument team here, which is, I don't know if you guys understand that, but being the head of an instrument team, that's a serious position. And she did so well there, obviously, that they put her in as project scientist now for the for Webb. She likes to bike and exercise, and she says she has a love for black and white film noir movies, which I also share. So we had a fun chat a little before. And because she grew up in Seville, she said that she learned to do flamenco when she was young, but of course she didn't really learn it professionally or anything. But maybe we can get her to demonstrate a little bit. Anyway, ladies and gentlemen, Macarena Garcia Morin.
Thank you very much, Frank. Just checking, can you hear me okay?
Yes, everything sounds
Yes.
great.
Perfect. Well, thank you for the kind introduction. I really appreciate it. And of course, thank you for having me. I'm really excited to be here to talk about the incredible science JWST is producing for all of us to enjoy. And obviously, thank you to everyone who connected. I'm really looking forward to our session today. So in this talk, I'm gonna talk a little bit about the mission, just like a very short reminder, and then we're going to deep dive into the science. And I wanted to tell everyone that this is, of course, a limited time. So there will be things I cannot touch. And if someone is listening and they don't hear their favorite topic or their favorite publication, apologies in advance, and we'll have the opportunity to talk about anything about science or the mission or whatever you want after the presentation. So let me start by talking about the most important piece of JWST, if I manage. Yeah, and that is the people. So JWST, it's the most sophisticated, amazing mission we have ever put into space. And to do that, it took decades of work. It took about 20,000 people coming in and out of the mission and working very hardly. And it took three different agencies, NASA, the European Space Agency, and the Canadian Space Agency. So this map is just obviously not to read, but all those little dots you see spread across the world, many of them in the US, they represent institutions with many, many people behind them that made it possible for us to today enjoy as much as we do the mission. So for me personally, the people are the key component of JWST. So what is JWST? In a really, really small nutshell, it's quote unquote simply a large infrared optimized telescope. And there are two things here that are important. First of all, it's big. It has a primary mirror of 6.5 meters, about 21 feet. And that means that because it's so big, you can actually detect very faint objects in the universe, and you can also detect them in incredible detail. Of course, the ones that are closer, you'll see the detail later. It is really astonishing. But you can also detect amazing detail on objects that are incredibly far away. So that's piece number one. It is big. Number two, it is on the infrared. So the infrared is a portion of the light we cannot see. It goes a bit red than our red, the one we see in the visible, and it has really interesting characteristics from a point of view of astronomy. So it is very good to peer through the dust. So we're not affected by that blocking of the dust that doesn't allow the light to go through. It's really good to observe cold objects because everything that has a temperature emits in the infrared. That includes ices, as we see with JWST. We see interstellar ices, we see cold planets, we see everything essentially. And it's also really good to observe the very first or the oldest objects in the universe. And that is because when those objects emitted their light in the optical, when they were created, the light started traveling in a universe that expands. So if you envision a slinky where you actually pull it, so that light will shift from the visible to the infrared so we can measure it. It is about 1,000,000 miles away. I'm not going to go into the orbit details, and if you're curious about any technical detail, we can discuss them later. So this is today. Let's go back a little bit to the inception of the mission. So as I said before, it takes decades to put these missions together, and the early ideas that are captured, or the earliest ideas that are captured, were in this workshop that was hosted at the Space Telescope Science Institute in Baltimore in 1989. Remember, this was about a year before that the Hubble Space Telescope was launched. So back then, all those scientists and engineers who were together, they were talking about the next generation of space telescope because they wanted to discuss what is next. And they concluded that the next thing to do was a large infrared telescope that would allow us to see the very first galaxies, among many other things. But observing the early universe was the primary science case for which the telescope was built. And then, of course, you can use it for everything because it's really flexible. To your right on the screen, you have one of the earliest design concepts back in 1995. And even though it's not what we have today, it really has all the components. It has a sun shield to protect it from the sun, from the radiation of the sun. It has a primary mirror that deploys. It has the instrument. It has everything that we have now. It's just an earlier, I think it's actually one of the first drawings ever produced for the telescope. So let's then move forward. We go from the late 80s, early 90s to 2021. We launched JWST on December 25th, 2021 from the French Guiana. And it was a really beautiful launch, very well optimized. It was perfect. And on the top image to the right, you do have the moment where the telescope separated itself from the rocket and started its travel towards the point where it's right now orbiting around the L2 point. And that was it was really fast. It's a few minutes after the launch. And it was really emotional for everyone who was seeing it because it was beautifully separating, and shortly after it did deploy the sun shield. No, the solar panel, not the sun shield. A few hours after that, all the communications that they were handed over to Space Telescope Science Institute in Baltimore, and there you have a picture of the control room, where for about 6 months, dozens of people were working on every aspect of deployment, switching on the instruments, making sure everything was correct, making sure everything was ready to start science. It was a very intense period, and that snapshot is just my representation of what was going on. We were switching things, so we were measuring temperatures, we were just checking everything. And finally, you have there our first alignment image. This was just an evaluation image, but the moment we saw that, it was very clear that, as we know now, the telescope was functioning beautifully. Like, all the data is incredible, the sensitivity is excellent, it's really beyond expectations. And you can see that, so you have the star in the center, and every little dot, every little spots that you have are behind the star, they are galaxies. And this was a really short picture. I mean, we didn't take a lot of time for this. So from the get-go, we knew it was going to be incredible. So 6 months after launch, give or take, we did have the release of the first images of the telescope. This is one of the most popular ones, I think. It's the Cosmic Eclipse, the Carina Nebula. It is beautiful. You see the detail, you see the power of the infrared, because you actually don't see that much dust. You see lots of stars, you see radiation. It's really demonstrating that JWST is indeed fulfilling its promise to revolutionize astronomy. So let's talk about science then. Because the primary science case for this telescope was to really observe the early universe that we couldn't do otherwise, because we needed this big infrared machine. I thought we could start with a brief reminder of the cosmic timeline. So everything starts with the Big Bang. And I normally, instinctively, because of the name, I guess, I think of the Big Bang like a big explosion, like, like in a movie, like explosion. But it really, cosmologists describe it as something that happened everywhere at the same time. And right after the Big Bang, like seconds after, we started, something called inflation started, where the universe started expanding incredibly quickly at an exponential rate. After that, like 400,000 years after that, we start having hydrogen, and we do have the cosmic microwave background. And after that, the universe becomes opaque. And that means that it was still expanding, it was cooling down, and photons couldn't actually travel towards us. So that took several 100 million years. We don't know exactly how long it took. We'll talk about that a little bit later. But at some point, we started having galaxies started to form, and galaxies had stars, and that's where the universe as we know it today started. And that is the all those little yellow dots there surrounded by brown structures. These are galaxies and their ionization bubbles around. So this means that these galaxies, they started to produce stars, they started to produce photons, and those photons were ionizing the medium around, and they could travel towards us. So these bubbles are representing that ionization. And then as time goes on, ionization gets more and more, and you have more and more bubbles. And finally, about it's about 900 to 900 billion years to 1 giga year that it really finished, and then we started to have the universe as we know it today. So that period with ionization bubbles is called cosmic ray ionization, and when it finished, we have the universe like today. Okay, so I'm starting here with just a list of bullet points, very simple, and then we're going to go one by one. I really wanted to emphasize the studies of the early universe, because it's really first the primary science case, but also one of the cases that it's very high profile, and everybody's really interested in that. So what has JWST found exploring the early universe? So very quickly, it has demonstrated the existence of very early galaxies, and we're going to see next which one is the record holder. It has shown that galaxies are brighter and more numerous than expected, so we have a lot of them, and they are also more developed than predicted. Not only we find actual structures like spirals and bars, but they are chemically evolved. It didn't take a long time to actually create additional elements that were not hydrogen or helium. We find many supermassive black holes and sufficient sources to transition from that opaque universe to a transparent universe, that reionization. There are also, we of course have still open questions, and thankfully none of this is solved yet, because that's why we launched the telescope, to learn all these things and to understand everything. But if you're here around in media or in anywhere that JWST has broken cosmology, it actually has not. It's just challenging our understanding of the early period of the universe and the science, and it's giving us additional pieces to really complete that puzzle of the first billion years of the universe. So this is the galaxy JWST. This is the oldest galaxy we've seen to date, and it has been measured with JWST with the NISPEC instrument, and it demonstrates that luminous galaxies, because it's really luminous, were already in place 300 million years after the Big Bang. That's really not a long time. It's really a very infant universe, especially considering that the age of the universe is about 13.8 billion years. If you look at the little inset there's an arrow because the image is showing two different galaxies. The red one is the one that is placed at about 300 million years after the Big Bang. The one that is pinkish is more as a projection effect, and that is not part of that galaxy. How do we know this? How do the scientists that came up with this amazing discovery know this? Well, because they use the power of a spectroscopy. And this is what you have here to your top right. This is a spectra. You observe the galaxy, disperse the light, and look for that feature, that sort of jump here, if you can see my mouse. That jump is called the Lyman break. And that happens naturally in every galaxy because galaxies emit very little before that break, essentially, and it doesn't come towards us because the hydrogen blocks it. So if you see that break and you measure it, you actually can determine how old the galaxy is. And as you can see here, the break is beautifully defined, and yeah, it's measurable. Not only it was seen in the near infrared, but also in the mid infrared, which is what you have on the bottom right panel. So it is confirmed, and it's really probably not the oldest. Probably this record will be broken, but it's been really groundbreaking to see that early after the Big Bang, we already have galaxies. I said before, galaxies are brighter and more numerous, and this is kind of a boring plot. It's not a beautiful image, but it really has a lot of information. So in blue, and let's focus just on the top one. In blue, we have about 60 sources pre-JWST, before that we had measured the oldest ones, and we are covering between about 930 mega years to about 420 mega years. So we have a bunch of them, and they are not that bright. So in this plot, when you go to the bottom of the plot, it is brighter. With JWST, you get all the orange points. So we have more than 1,300 galaxies from JWST that have been measured, that have been confirmed, and that really are demonstrated that we thought perhaps we had a picture of how these galaxies would be, and we're finding a lot more, and that they are to be really brighter. And really now it's a matter of understanding why these galaxies are this bright. Is it maybe because they have really lots of massive stars? Is it maybe because they are clearing up the dust and they are really bright? It is still a process, but this data will definitely be key to solve it. These galaxies are old, but they also have metals. And remember that when we talk about metals in astronomy, we're talking about everything that is not hydrogen or helium. And as you can see in this spectra, the light is dispersed, and all those little bumps that you can see with labels, they are what we call emission lines, and they are different elements that have different ionization. So we have oxygen, different types of oxygen, we have hydrogen, we have neon. So this is telling us that even a galaxy that, like this one that was formed 500 million years after the Big Bang was measured, we already have metals. And this, well, first of all, is quite early in the universe. And second of all, let's remember that these measurements were impossible before JWST. And seeing these clean emission lines again, every time I see it, it really blows my mind because it is just fantastic to have this data at our disposal. So many galaxies, they are bright, they have metals, and they are chemically rich. And that enrichment happened relatively quickly. In addition, JWST is finding many accreting supermassive black holes, and it's really perfect that Frank talked about black holes right before this, because it gives a very nice context. So I put here just two of the examples. To the left, you have a black hole. It's a candidate because this was measured with X-rays, with an X-ray variation with Chandra, and that sort of blip happens to align with a galaxy that is at a redshift of about 10.3, and that is really, really massive. So again, this is very early in the universe, less than 400 million years. So at this early stage, having a black hole that is so massive, and we're talking about masses of about 10 to the 7, 10 to the 8 solar massive, it is hard to explain. And having a stellar black hole seed that accounts for this, it is close to impossible because you do need time to develop those stellar black holes. So there's a question mark on this one. To your right, if you have another demonstration of this is a demonstration of a black hole, because if you see those emission lines, you have ones that are narrow and you have ones that are broad. And the broad ones are a demonstration that there is an AGN, or active galactic nuclei. So that means that at the core of that galaxy, there is a black hole that is accreting and that is active and that is perhaps accounting for a lot of the brightness. And this is a black hole of about 10 to the 8 solar masses. Again, really, really massive, that we need to explain and are kind of unexpected. And the explanation could be something like massive seeds or rapid black hole growth. So nothing out of the box in a way, but that has to be confirmed and really studied carefully. And for that, we need just more data, essentially. Okay, so going back to that little diagram we saw before, we were studying the JWST is studying the epoch of reionization. It started a few hundred million years after the very Big Bang, and it turns out that with JWST data, we are seeing that the sources that we're measuring, they are sufficient to account for the reionization. And on this plot, you have little red stars and white stars. So the red stars they are Lyman alpha emitters. So essentially, they represent galaxies that are forming stars, and they are producing ionization photons, and they can account for the reionization as we are seeing it. So that's that data is consistent with what we're seeing. And around each of these little groups of stars or galaxies, you have a blue glow. That blue glow is representing the ionization bubbles we're talking about. Those ionizations bubble up there that will end up taking over the whole universe and having a universe transparent as we have it now. Of course, like in every good situation, you have many questions, and we still have many things that are, apart from these ones that I have mentioned, there are other things that are still under study. And one of them, you maybe have heard of them, is the famous little red dots. And the little red dots are, you see here a sample of them. So they are very red, compact sources. And when I say compact, they're really small. They are about 100 times smaller than the Milky Way. And their nature is unclear. Some studies indicate that they are active galactic nuclei, so they have a black hole in the center, and that is accounting for a lot of the emission we're seeing. Other studies indicate that they may be all the stellar population, so we don't have a unique answer, and maybe the answer is not unique. Maybe the answer is a combination of both. But again, we need more data with the two sort of near-infrared and mid-infrared to reconcile the results, and perhaps even using other facilities. So this is going to be a really interesting puzzle to solve. And then, of course, one of the, in my opinion, the big and additional open question is the cosmic dawn. So the cosmic dawn is that time where galaxies started to form, and they they started to reionize the universe. And here you can see it marked with in this plot, in this diagram, is marked at about 200, 300 million years after the Big Bang, but with a question mark, because we really don't know. And how do we locate the cosmic dawn? So essentially, you have to locate systems, and by systems I mean galaxies that are chemically pristine. So systems which represent the first generation of stars. So that generation of stars that was formed pretty much with hydrogen, helium, and they're very chemically clean, if you will. They haven't had the time to get rich. There have been already claims of population 3 stars. So I mean, you have a few references in here, but with JWST, but they are not fully demonstrated. So as of today, no one can say, okay, they have been found in this galaxy, so this is where it all started. So we need more work, because proving this with data, it's really difficult. The burden of proof, as I heard Richard Ellis saying recently, it's really high, because, for instance, those very early generations of stars, they may evolve really quickly and get mixed with population 2, that is the next generation that has a little bit more metals, and that would make it really hard to measure and to determine. So fun times for people who work on population 3 stars and 2 stars and really get more data and more answers to all these questions. If we leave a little bit that very, very early universe and move to a closer universe, which is still very young, so we're talking at redshift of about 3 and 4, couple of billion years after the Big Bang. So to your left, you have this slide. It's just talking about, at that time, about 2 billion years after the Big Bang, we are seeing population of galaxies where the star formation has stopped, essentially. Not much is happening in that area. So they are faint, they are old, they are massive, and they are quiet. They are not forming a lot of stars. And the plot to your left is just a few spectra where the researchers have demonstrated that for these galaxies, including for the oldest one, that is about 2 billion years, about half of the life of the galaxy, it has not been forming stars, which is really interesting. And to your right, you have a similar plot for another galaxy. All those absorption features or those indentations that are fitted with a black line with a model, they are indicating that the stars in there are old and that the galaxy is kind of quiet at this point. So an interesting point that I like to link with a much closer galaxy. So this is a very nice animation of the Wolf-Lundmark-Melot local group galaxy. So we start with a ground-based observation of the galaxy, and now we're zooming in, and you're going to see a really beautiful image taken with a NIRCam instrument. It's a near-infrared camera on board of the JWST. So for this galaxy with NIRCam, JWST has charted the star formation history of the galaxy. So what does this mean? This means that they have counted on the data all the stars, one by one, that belong to this galaxy, and they have put them in this diagram. You see thousands and thousands of points. So this diagram represents, it's a temperature versus brightness diagram. So all these stars in here represent, when you look with the models, you can determine their ages, you can determine their status of evolution, you can determine the temperature and the brightness. And so with that, they can model when events of star formation happen on this galaxy. And they have close at 600,000 stars in there. So there is a lot to unpack. But if you look at the plot on the right, essentially what they find is that this galaxy, after the epoch of reionization, so once the universe was transparent, suddenly the star formation stops. It has a pause, and this pause is quite extended. And then after a while, it starts forming stars again, and then a pause, and then it forms stars again. So you see that in this sort of, it goes up, and then it flattens, and then it goes up. This is what we call the cumulative star formation history. So you are characterizing these stars, seeing when were they born, how old are they, and how they can fit with the models that they are using. And I find it a really beautiful connection with those galaxies that are really old and that are also seeing their star formation suddenly stopped. I think there are quite similarities that we're learning with this much new, closer galaxy. Talking about galaxies, galaxies have clusters, and clusters are fundamental to study star formation because they are stellar clusters. They form out of the same big molecular cloud. They form at the same time. They have give or take the same age, but they have many different masses. So they are like little laboratories of interesting star properties that are really well studied, and they are very useful. So with JWST, we're tracing the star cluster formation across cosmic time. So what does this mean? If you look in the background, and if you remember, this is the SMACS 0723. This was the first image that was revealed in 2022 by President Biden. And it is a huge galaxy cluster. So if you imagine a large galaxy cluster, everything that is behind the cluster, when the light travels towards us, it bends around the cluster because it's so massive that the light behaves like a particle. So it's just bending and creating mirror images of whatever is behind. Not only creates mirror images, but it also It's like a natural telescope. It does amplify them. And you have here a few examples. All these arcs and all these structures here, they are just galaxies that happen to be behind the cluster and that we can see much, much bigger. And I want you to focus on this little one. Someone named it the sparkler. I think it's a beautiful naming. It's very fitting. So this is a galaxy. It is very distorted because we're seeing like a mirror image. But all these little dots around it, they are clusters. They are star clusters in that galaxy that before now we have never been able to see in this detail for galaxies that are that old. So this is another view of the sparkles. So you have the sort of tail is the galaxy, and all those little dots around are incredibly detailed. It's just, incredibly detailed stellar clusters that we have measured with JWST. So when the science team that looks into this data study them, their ages indicate that the precursors of these globular clusters, they form around 9 to 12 billion years ago. So they are really, really old. And now we're able to measure them and study them. So what does this mean? This means that we have a window into star formation really back in time, thanks to the power of gravitational lensing. All right, let's talk a little bit more about galaxies. So now I want to have a nice connection with the Hubble Space Telescope. So I remember before launching JWST, often people will ask, well, JWST is a successor, and well, it's not, because they are very different. HST looks primarily in the ultraviolet and the optical, JWST is infrared. So there is a synergy, and that you can see in this beautiful image. So this is a galaxy IC5332, as seen by the Hubble Space Telescope. So you see you see the nuclear, you see the spiral, it's a face-on galaxy, lots of stars, lots of dust. All those dark arms, spiral arms, they are very dusty. If you look at it with the JWST, this is what you look. So if you see back and forth, it's really same galaxy, but tracing really different things. So with JWST, we see that sort of spidery structure full of cavities, and those cavities that have been created by events like supernova, and they get cleaned out and they get empty. And then in that process, they also compress the gas, and you see all these bright structures here. These are newly forming stars. So again, HST and JWST is a powerful partnership, as these beautiful fangs images demonstrate. So this team, this was a release this year. It's a fantastic data set. They have a collection of face-on galaxies, and they use the JWST data to reveal the physics of the star formation, the feedback, and by feedback is like sort of the energy that comes and goes from the AGN to the galaxy, etc. The explosive activity, such as supernova, and how the gas dust cleaning associated to the stellar activity impacts the cycle of a star formation in nearby galaxies. So I think this is one of my favorites personally. It's really beautiful. Right. So you can do many things with galaxies. And for instance, with galaxies, you can study the Hubble tension. And the Hubble tension is, so we know the universe is expanding and we know that it's accelerating. And when you measure the expansion velocity with different methods, late times versus early times, you get different results. So this is the Hubble tension, essentially. Different methods to different numbers. So with HST, years ago, Adam Riess, which is a Nobel Prize laureate at the Space Telescope and Johns Hopkins, he showed that with Cepheids, that are variable stars, they're really good for measuring distances. He did show that the Hubble tension existed, essentially. He confirmed that. But there was a question of, is it maybe that the HST data it is a bit too crowded, as you can see here? And then, so he went back and he used JWST in the infrared to go back to the same data, same galaxy, observe the Cepheids and supernova, and really estimate distances and compare with the HST results. And what they get is, well, it's not as crowded. The data is more separated and sort of quote unquote easier to interpret and manipulate, but the result holds. So the Hubble tension is still there. When you measure it with these techniques of using Cepheids or supernova or any other, some other candidates that other groups are using, when you measure them with earlier times indicators that are observables, and then when you compare that with, late indicators that are observable, when you compare that with other measurements, not measurements, other estimations of the expansion of the universe with the cosmic microwave background and theory, the results are different, and that's the tension is still there. So again, HST and JWST having a great partnership and confirming each other results, I would say. And more to come on this. Right, so galaxies are the neighborhoods where we have stars. And JWST is also deepening our insight on the life cycle of stars. I wanted to start with this beautiful diagram that shows in a really quick way what is the life cycle of a star. So you start with a star-forming nebula. That's a cloud with lots of gas, lots of dust that at some point starts to collapse and form stars. And you have, broadly speaking, two types of stars. And the life of a star and the death of a star, they depend on the mass. So if you have a star like the sun, approximately, that star is going to live for billions of years. It will end up like a red giant. Finally, at some point, that sort of fight between the gravitational collapse and the expansion, it will expand itself because it has like a little nuclear engine at the center, well, a big nuclear engine at the center. So that fight between the nuclear engine and the gravitational, it will sort of shed all the outer shells and end up like a planetary nebula that will dissipate and it will end up like a white dwarf. And finally, it will sort of, many years later, sort of switch off. If, on the other hand, you have a really massive star, about 8 to 10 times the mass of the sun, or even more than that, the life of the star is really fast. It's not billions of years, it's more millions of years. That for a star is really quick. And the more massive, the faster it goes. And they will end up as a supernova. And then depending on the star, it will end up as a, for instance, neutron star or a black hole. There are many types of supernova, but essentially they explode and they may end up different ways. The interesting part is that no matter what type of a star you are, you will end up enriching the environment. You will end up creating, the supernova will end up creating really, really heavy elements. And they will also enrich the environment and give the materials for the next generations of stars to form. So from that diagram to this beautiful image, very recently published of the Serpent's Mane, this is a cloud where we have a lot of protostellar outflows. So when a star forms, stars forms from clouds. And I hope you can see it, but in this image, there are many line-like structures. Like if you start from the center, you have these outflows and you have them everywhere, if you can see my mouse. So all these sort of outflows, the investigator team in this case, they have a study. I think there are between 10 and 20 of them that you can easily see. So when stars form, they form from a cloud and that cloud is rotating. And there was always the idea that when the cloud rotates and the star forms, the protostellar disk and the jet, they will keep the same sort of rotation. And the incredible result of this is that they are seeing that for most of these jets, they are relatively well aligned, indicating for the first time that yes, probably they are preserving that initial rotation from the cloud, and that's seen in the way the protostellar outflows are behaving. This is an example of a planetary nebula. This is the future of our sun, for instance. It will sort of shed all those external outer shells and it will just enrich its environment to end up as a white dwarf. And here, what JWST is giving us is this incredible detail, really, really incredible detail with all the shells and the dendrites and the structure that can be studied and used for understanding better the stellar evolution. On the other end, we have supernovae. And we're going to see two types of supernova here. The first one, this is a very famous supernova. This is Remnant. This went off in 1987, and it's been followed up for many, many years. And whenever an astronomer goes back and observes it, it has changed because it is obviously expanding and changing. So JWST has, for the first time, provided evidence of a neutron star at the center of this supernova remnant. And this is thanks to argon measurements that they are there because there has to be a source of high energy radiation, and most likely it's a neutron star. And if you remember, the neutron star is when very massive stars explode, you can have neutron stars or a black hole. So in this case, we have a neutron star for the first time seeing in this supernova. This is another. It's not an animation. This is actually based on real data, and it's a beautiful example of the Crab Nebula supernova remnant. This supernova went off more than 1,000 years ago, so it is like it has had plenty time to expand and evolve. And different colors here have different meanings. So in blue, we are tracing, well, in red, that is here, we're seeing dust, and this is traced by different filters. In green, we see sulfur. And then when the blue comes in, what we're seeing is synchrotron radiation. And synchrotron radiation is essentially, we are tracing particles as they move around magnetic fields, because we have a pulsar at the center of this supernova. It's a different type of supernova than 1987A. So again, a beautiful example of a really. This supernova went off more than 1,000 years ago, and yet we're still studying it and learning and putting the pieces together of what stellar evolution is. Okay. We have stars, and as we all know, often around the stars we have orbiting planets. I really like this diagram, this artist impression in this case, because they have put the star there in the corner with its disk, and the star is formed. And there is a protoplanetary disk, because when planets form, they have also their little protoplanetary, circumplanetary disk going around. And in this case, they are, for the particular planet, they did this artist impression. It has a moon, which is this little thing here, but this is not with JWST, but it's still very beautiful. I find it very endearing. And also the fact that they're clearly saying, okay, there is a planet forming and it has its disk, and then the star has like the bigger disk, and you have all those motions that often will clean up sort of tracks in the stellar disk to make the planets. So a couple of examples of JWST, because exoplanets are clearly one of the top science cases for JWST, and I would say in general. And it's interesting because when the mission was conceived, exoplanets were not, we didn't know they existed. There was no proof that they existed. So right now we have more than 5,000 exoplanets cataloged, and it is a really blossoming field. I would say, no blooming. It's really lots of interest, and lots of data is going into that. So this is not yet a planet. This is a young protoplanetary disk. So this is what we call a photodissociation region on Orion. This is the Orion bar. And what's happening here is we have, to your lower right, that orange part, that's like a molecular cloud where stars are forming. You have young stars coming out, and you have lots of material. And on the top left, there is a trapezium cluster. So there are lots of young stars there that are irradiating this region. And on that irradiation, they are creating winds, and they are impacting the chemistry of those regions. So the incredible result of this team from the PDRs for all ERS team is that they detected methyl cation, which is CH3+. And why is this interesting or important? And they detected it in this protoplanetary disk that you have here on the bottom right. And if you're wondering why the disk looks like, the shape is kind of odd, it's not circular, it is because of all the radiation that is hitting it is like a wind that is sort of deforming the shape. So anyway, going back to the methyl cation, this molecule, it's like a building block. It is a building block that is used at that. It is like the basic to then build up more complex organic molecules. And the interesting part here is that it is present in that disk, in that protoplanetary disk, because the radiation from the stars is allowing to create the necessary energy and conditions to make that methyl cation possible, and then further down actually create more complex molecules. So really interesting. And why do we care about these things? Well, we care because the protoplanetary disks contain the elements and the ices or the organic molecules. Everything that is in there are the ingredients that will be used to build up the planet. So that's why there is so much interest on studying them. And this is what this slide is about. So JWST is really making it possible to bridge the chemical inventory of disks. So what are their compositions, what is actually contained in there, and the properties of exoplanets. And that there are many different types, and that is like marrying those fields together. And I have to say, when it comes to protoplanetary disks and disks in general, JWST provides, as you see in this spectra, this dispersed light, like a forest of information. All those lines are molecules and they contain information. It's really rich, really rich. Right. From a protoplanetary disk to actual planets that are being formed and studied. So broadly speaking, we have two types of planets. We have gas planets, giant gas planets, and we have rocky planets. This is really kind of a separation, and we normally do. JWST has provided the first detection of many molecules in giant planet atmospheres. And this is just an example quite early in the mission. This was 2023, but it really shows that with the combination of JWST plus all the models that are necessary to interpret the data, we have really identified water, sulfur dioxide, carbon dioxide, CO, CH4. So there is a lot of information in there, and it just keeps on going. So this is for gas planets. Not only we are looking at composition, but there is also more and more emphasis on characterization. And this is an example, again, a really nice results from very recent. This is a planet, is WASP-39b. This is a giant gas planet. And it is an interesting one because it's tidally locked. So it's not like Earth where it rotates and day and night they go around the world. In this case, day and night are always happen on the same place. It rotates sort of locked with the star. And this investigator team, they did a really exciting result because they were able to measure differences in temperature between the evening and the morning side. And interestingly, the evening side was warmer because of the clouds and transitions from the morning. So lots of characterization. Each time one of these exoplanets is characterized, it provides a new piece of information that then is shared and contrasted by the others. From gas exoplanets to rocky exoplanets. And rocky exoplanets are really challenging to measure. And the quote-unquote holy grail is always to find a secondary atmosphere. It's difficult. It's difficult because it's a faint measurement. You have to find the signal-to-noise ratio. You have to have the right models, but you also have to be careful of the impact of the stellar contamination that can actually contaminate the data of the planet. So even though of the challenges, there's already one groundbreaking discovery, which is a secondary atmosphere in a rocky exoplanet called 55 Cancri E. And this is an atmosphere that can be outgassed from and sustained by a magma ocean. So it's like really I just can picture it like a really hot planet with a magma ocean that is feeding the atmosphere. And here you have the points, the yellow and purple points are near infrared and mid infrared data. And the blue and the red line are the models. And so you see how the model that fits best is a a model that considers that the planet has a volatile rich atmosphere. I didn't mention, but a secondary atmosphere typically for exoplanets is defined as an atmosphere that is not the primary when the planet is formed, but it is an after effect of activities such as volcanoes, etc., and in this case, magma. But it's also a good representation of the fact that for many disciplines in astronomy, and exoplanets is no different, the precision and the high quality of the models and the need for models, it's really important, because the data by itself, it will be there and it's solid, but you then need to interpret it with the right model. So it's a really flourishing field as well. Finally, and I didn't add a lot on the solar system because of the timing, but obviously JWST has observed the solar system in great detail. And the solar system, to begin with, you could think, why would you want to point a 6.5-meter space telescope to something like Saturn or Jupiter that are bright and big? And the answer is yes, because you get incredible detail. And you also, even though these planets are bright and big, they also have faint structures, and they also have moons, and all of those are being studied. And not only moons and planets, it's also near-Earth asteroids, main-belt objects, comets, everything in the solar system that can be observed. So from Mars and beyond, it is being observed with JWST. And here you have a few examples where you have on the top right, the measurement of endogenous CO2 in Europa, so formed in there. You have data from Saturn, where you can see the atmosphere and the changes and the clouds, and you also have data from Jupiter. And of course, here in the center, a beautiful image of Uranus with lots of moons. Right, so to wrap up, I wanted to show a beautiful video that was produced by our Office of Public Outreach based on the second anniversary image. I don't know if you saw it, but this year the anniversary image for JWST was this very nice and endearing interacting galaxies called the penguin and the egg, although some people call it hummingbird or squid. It depends on what you see, but here's the penguin, here's the egg. These are two galaxies that originally had similar mass. There were two spirals, and they have been interacting with each other. And on the process of that interaction, it has changed the shape, and this is one of the galaxies, and this is the other one. It has really distorted and created this really interesting shape. And I'm going to play the video because it provides additional depth and interest to the data. It's really nicely done. So here on top, you can see that what you would see is the eye of the penguin. It's actually the nucleus of one of the galaxies. And all the arms are distorted and creating a star formation as a result of the interaction. Well, this was my last slide. Just to wrap up, incredible results. The observatory is working really much better than we could dream before launching, for many reasons, many technical and good work reasons. And the science is there, a lot to unpack, a lot to keep observing. And many of these results, what we need to do now is just to get more data and to keep interpreting it. I'm going to stop sharing.
All right. Thank you very much, Maka. That is a wonderful summary of just 2 years, only two
Just
years of Webb Space Telescope data. And so I guess one question the public might have for you, I mean, because Hubble's been around since 1990, so that's 34 years now.
yeah.
How many more years of amazing Webb data do we have? Because it's an infrared telescope and it has, different constraints on it. So what can we expect? 10 years? How much more?
We can expect at least 18 more years, and I'm going to give a
Okay.
reasoning for that.
Okay, great.
And the reason is that during launch, it was so optimized that we did save fuel.
Yes.
So that's the fuel we need to keep it in orbit, just doing minor corrections.
Right.
And so the more fuel we have, the more we're going to stay in orbit. And the estimation is about 20 years, which is a long time. And I'm sure that our, you know, flight operations teams and flight dynamics, they will optimize it to the last drop of fuel to keep it going. And then, of
Yeah,
course, mechanisms age, things will happen, but we do have ways of maintaining it for as much as possible there.
right. The inventiveness of people in maintaining these telescopes has been fantastic. Hubble is now down to reduced gyro mode.
Yeah.
Okay, so they have done fixes and things that uh I didn't think possible way back in the 90s when we launched Hubble. So
No,
um,
it's really amazing. Yeah.
quite sure that the inventiveness will be no less for Webb. So, what strikes me about the amazing discoveries that we've gotten since I did my PhD in cosmology is
Great.
basically looking into how quickly we're developing these galaxies. And I really, to me, I would call them proto-galaxies because this is, not really a full-fledged galaxy like our Milky Way, but it's more of a dwarf galaxy type size. Um, One member of the Jades team, Kevin Hainline, is actually in our audience tonight. I saw
Oh,
him
then you
chat.
should talk about that.
I know. I asked him a question in the chat, and so he gave me the estimation that the Z14 galaxy from Jades is about half a billion solar masses,
Yeah.
500 million solar masses, and so we're getting 500 million solar masses forming in 300 million years.
It's
Um, yeah, go ahead. Just
no, no,
your
no, no. Well,
reaction on
first of
that.
all, since Kevin is online, congratulations on the result. It's really mind-blowing. I love seeing the near spec and mirror data there. It's really amazing. And yeah, so now the question is how these galaxies came to be, that quickly.
And one more, you also mentioned that we're getting supermassive black holes very quickly,
Hmm.
which also goes into that structure formation is happening sort of faster than we thought possible, really. Certainly during my PhD work back in the 90s, yeah, we didn't think that such like this was possible. Um,
Frankly, if you would have asked me before launch, will Miri be able to detect with this level of quality galaxies at redshift 14? I would have been like, I don't know about that. I'm just blown away by everything. Yeah. But also it's really neat to see that, we don't know everything. And that's a good thing. That's why we launched this telescope to
Yep.
really get more data and understand better.
Okay. Well, we have had a lively discussion in the chat. So Grant has been monitoring the chat. Grant, why don't you turn on your video? Say hi to everybody.
Hi.
Hello.
I saw a couple interesting questions in the chat. You get to choose them. So
All right.
tell us what your favorite questions are.
Well, I'm starting off with a Miri question since we're just talking about Miri. Um, how is it that Miri filters out the wavelengths other than the ones that you're looking for your purposes?
I'm sorry, can you repeat the question? How is
How is
that?
it Miri filters out the other wavelengths or gets rid of a lot of the noise to get you the spectrum that you're looking for when you're doing your observations?
Okay. So if you're taking images, you have, for both Miri and NIRCam, you have a set of filters. So when you have a filter, you essentially use materials that filter only that light. For instance, in Miri, we have filters from 5 to 25.5 microns with a different broadband. And so with the materials used in the filter, like semi crystals and with the right properties to only filter those lights. I mean, it's not perfect. You have like a transition, like a filter curve that you can characterize, but it is a physical blocking in there. For the spectra, what you do, we have different flavors. So you can disperse the light with something like a prism or a grating. And again, you do a selection. So with a prism, we select from about 5 to 12 microns. 14 if you're generous, but nominally is 12. And then you disperse it with a prism. And it's really only that. There are sometimes there are contaminations from other orders, but we can take care of those. And then with our integral field unit, it goes from 5 to 28 microns, give or take. And again, you use a combination of essentially gratings and the light. I mean, I don't have it in here, but we have engineering diagrams that show how the light bounces and how many times has to bounce and how many times you have to break it up and make different rainbows and dispersers to actually get to it. But it is done with the hardware.
Yeah.
It is done mechanically.
And I would say this is a really important misconception the public often has about filters, right? In English, we talk about looking at the world through rose-colored glasses, right? And actually, a lot of the public thinks that, oh, you're adding red to what you're seeing, which is absolutely not what you're doing. Instead, what you're really doing is you're blocking every other color but red. And so the public doesn't have a great feel for how filters work, that it's blocking all the other lights and only letting through the light that you want to observe. And this is really what our telescopes are doing.
Exactly.
Okay, what else we got?
Yeah, bring us on to the next one. How does JWST help us to understand in regards to the composition of plasma jets that was not possible with other telescopes like Hubble or Chandra?
I think I'm not a plasma jet person, but I would say that it goes back to being able to do measurements in the infrared that you were not able to measure before. And if I can take an example of a jet that is coming to mind now, it's like when we saw before the protostellar. It's not a jet, it's an outflow, but it's like a similar thing. So a similar structure. So what you see there is an incredible level of detail. Now, when the person is saying plasma, I don't know exactly which type of temperature or at which wavelength we will need to look at it. But yeah, if visible with in the infrared with Webb, it would be all a matter of sensitivity. You will see different structures and you will see a lot of detail.
Yeah, and anybody who's interested in the jets that JWST sees, go look at those protostellar jets that we have seen. I mean, you're seeing through the dust clouds and you're seeing those protostellar jets. And there are several really great images that we've released on that. They've blown my mind.
Yeah, actually, if I may add, go back to the first anniversary image. Amazing collection of protostellar jets. It was beautiful. Yeah.
Very much so. All right. Does the early appearance of metals suggest earlier star formation than expected, some other method for creating metals, or something else?
The honest question is that we don't know. There are many theories. So there may be, that we have very, very massive stars, like more massive than we can think of, and they evolve incredibly quickly and they enrich very quickly. We may have what they call a top-heavy initial mass function. Well, no, that's more for the brightness. We really don't know. What we know is that we have the data showing that those galaxies are there. They are that old and they do have certain metals. So there are a lot of studies that are going into things like comparing lines, deriving electron densities, seeing how that fits into the models and all that. But the honest answer is that we don't know what the answer is yet, which is fine because some of these, I think, when it comes to the chemical enrichment, the metallicity, the little red dots, for many things, I think we often, including me, I would like to have like a clear-cut answer, like, oh, it's this and not that. But sometimes the answer comes from different ways and it may not be that clear or clean. It may be a combination of factors.
Right. In particular, population 3 stars, how long is their epoch? I mean, is it only 10 to 50 million years, which is really, really hard to pick out from this far away in time.
Exactly.
I mean, if you could get a population 3 epoch that lasted 500 million years, well, that we could see.
Exactly. Completely agree. Yeah.
It's, it's always,
That's one of the challenges to actually, again, I think the demonstration of the present, the objective demonstration with data of the presence of POP3 stars will come from many different studies that will look at different objects and will collect different evidence. I mean, we already have, I show a few references on the slides, several publications saying that they have indications and they give background, but some of the explanations are not unique. You could have a different explanation that is not population 3 that could explain the data. So it'll take effort and time. So because I'm an optimistic, I say that's job security for many people. they get to keep playing with it.
What else?
All right. Where in your field, what is it that JWST has done now that it's in its second year that has surprised you, and what has it done that has more or less like not lived up to your expectations, or has everything simply been a little bit narrower a field than you were expecting, or a little bit more data than you were expecting?
Well, that's a good question. It has lots of aspects. So from the moment I personally saw the data coming down from the telescope, and from the moment that we started seeing the high quality of the optics, I mean, we all knew that we had something special in our hands, and that it's not living up to those expectations because it has surpassed them. And I think part of it, certainly for the image quality, I think we have a lot to thank to the segmented mirrors and how clean they were kept. Contamination was kept to a minimum. The alignment is really exquisite, and we have an amazing team taking care of that. So that's a big part of it. Something that has not, how can I put it? It's not lived to expectations because things happen. But on the mirror instrument, we have at the very long wavelength a little bit of, well, at the very low wavelength, we have a loss in throughput, and astronomers who are, if some are online and they will know this certainly. So at the very low wavelengths of MIRI, we have a little bit of less sensitivity, and that's something that, it happened relatively early in the mission, and we're tracking it, and it is being compensated by either integrating more or compensating with modeling the data essentially. But that's something that it happens because you build the hardware, you launch it to space, and then suddenly, we think this is a combination of impact of radiation with some hardware combinations, so that resulted on that. And it's only at long wavelengths, and it is already stable. But that's one thing that, you don't want to see it that early, but it happens, and it's been managed beautifully. And Miri is actually delivering incredible data. I think you also mentioned that the amount of data, it's overwhelming in the sense of the sheer amount. This is just what I would say a biased selection of the science results. I think they are very relevant, but many things I don't have the time to mention or even put in there. So that's apologies to anyone if I miss something incredible, because there's a lot of data. The community is incredibly active, and they publish and publish and publish. We have hundreds and hundreds of papers in a very short amount of time, which is a good problem to have, if you ask me. So, yeah.
I mean, I have to relate it back to the time when Hubble was launched back in 1990, and you just added that, factor of few in resolution that you didn't have before. I mean, Spitzer did an incredible job of surveying the sky in infrared, but the extra resolution from JWST has just changed your views on things, or just enabled you to see things you hadn't seen before.
Yeah.
And it, like the number of background galaxies we see in just random shots are just mind-blowing sometimes, because you knew it was going to be better, but yeah, it really is that much better. And so in terms of the science results that I've seen, every one of them seems to be pushing, that 10-20% beyond what we expected we were going to get from it. So that as
Every
a success
field.
point, yeah.
Yeah, I completely agree. Every field of astronomy, it's just pushing and plowing through with the JWST data. And I should also add that people from different fields have mentioned to me that they feel from the beginning that the models are lagging, because especially things like when you talk about the chemical makeup of protostellar disks or protoplanetary disks, when they got the data for the first time, it was like a forest of information. So the models are lagging in a good way, because now they are catching up, and they are really important. But yeah, it's an exciting time, I have to say. And this is only year number 2, starting 3, so more to come.
Oh, and you said we're going to go for about 20 years, so we got
Mhm.
10 times coming on this.
Yeah,
All
plenty
right,
of
great.
time. I think I'll finish us off with one more question. Is
Sounds
that good?
wonderful.
Okay. Returning user asked this one, so I'm throwing this out there because he's usually got some good ones. Okay. Sorry, 1 second. All right. Is it possible for nucleosynthesis to age occurred prior to any star formation at the earliest times after the Big Bang?
Nucleosynthesis to
Read that again, because I
Okay.
didn't
yeah.
quite
I
grok that.
think
I'm
I think there
sorry.
might be a little me reading. Uh, is it possible for nucleosynthesis?
Yeah.
No, that's what it says. To age occurred prior to any star formation. I'm guessing there's some typos here.
So if the person is asking, I'm trying to understand. So apologies if I'm not. If the person is asking, is it possible to create nucleosynthesis of chemical elements? I guess there's like oxygen,
Yeah.
nitrogen, etc.
Yeah, prior to star formation.
I think the answer with what we know would be no.
Yeah.
Okay.
Yeah.
I mean, because, yeah, I mean, in differentiating between pop 3 and pop 2, you will see the emergence of metals and everything, and that's the nucleosynthesis and the supernova explosions and everything, and the star evolution, stellar evolution stuff. So,
He's retyping it. Hang on just a second.
okay.
Okay.
It's on a delay.
I mean, because Big Bang nucleosynthesis obviously occurs way before any of
Yeah,
this
that's
happens.
like the
So,
whole
and
point.
that's sort of like an input
Yeah.
set of numbers.
We'll give him a second to do that, Frank, if you want to
So one
insert
of the things
something.
that while he's retyping, one of the things that really struck me was that you're talking about these quiescent galaxies between redshift 3, 4, and 3. Okay, and if I remember from my graduate school days, the peak star formation rate in the universe is somewhere around redshift 2. So we're talking about some galaxies that have already sort of like quieted off by redshift 4, between redshift 4 and 3, and yet most of the galaxies in the universe are, you know,
Yeah.
still ramping up to
But
hit their peak.
maybe after that quiet phase they will merge. We know mergers are a common phase of galaxies, and I really like that result of the local galaxy, the WML, I think it's a name,
Yeah, yeah.
where they see like star formation and then it stops, and then star formation and then it stops. I think it's very telling.
Hmm.
Um,
I mean, especially for a relatively small galaxy, if you get a lot of star formation, you get a lot of ionization that's going to
exactly.
heat everything up, and then it's got to take time to cool back down to collapse to form new stars. And maybe that's working on a galactic scale too, an intergalactic scale too, with the reionization of the universe.
Mm.
So that's a new perspective for me here.
I think we can probably end there. I don't think I'm getting anything else from the chat.
Okay.
Okay.
All right. Grant, did you have any questions yourself from what you're listening to the talk?
Oh, the JWST instrumentation question was mine. That was what I
Ah,
wanted to
okay.
know.
Okay.
I got mine
See,
in there already.
as hosts, we get to sneak in
Yeah.
our questions as we
You
like
get to
to.
choose.
All right. All right. Well, thank you very much, Maka.
Thank you.
Next month, everybody, on September 3rd, Ori Fox will be talking about the Roman Space Telescope, the next of the great observatories to go out. Hubble resolution, 300 million pixels per image. Yeah. We're talking about lots of data. This is going to be lots of data. Come hear about that. That's slated for launch later this decade. All right. Thank you for coming tonight. We hope you really enjoyed it, and we will see you next month. Take care.
All right, everybody's good. Oh, and now he corrects the questions.